Consider the incredible strength of a tiny ant. It can easily hoist 50 times its own body weight. An elephant, on the other hand, tops out at lifting about 10% of its weight. To put that in perspective, a healthy human sits squarely in the middle, capable of lifting roughly half of their own body weight. If an ant is that pound-for-pound powerful, it's natural to assume that scaling one up to the size of an elephant would give you an unstoppable, superhuman apex predator. But if you actually created a monster ant, its legs would immediately buckle, and the creature would instantly crush itself under its own immense weight. Nature doesn't scale in a straight line. To understand why a giant ant is a physical impossibility, we have to look at a mathematical trap discovered over 4 centuries ago. Galileo Galilei first identified this trap, outlining what is now known as the square cube law. Take this standard 1 centimeter cube. The flat face is its surface area, and the 3D space inside is its volume. If we double the dimensions to 2 centimeters, that surface area subdivides and quadruples, but the internal volume octuples, holding exactly 8 cubic centimeters. This is the core of the square cube law. As an object grows, its volume scales at a cubic rate, while its surface area only grows at a square rate. This rule governs everything we build. Architects can easily construct a small-scale model of a house out of paper mache, and the model will stand perfectly upright. If you try to build a life-sized house out of that same paper, the total weight of the structure, its volume, increases much faster than the paper can handle. The cross-sectional strength of the walls, its area, fails to keep up with the weight, and the structure collapses inward. This mathematical disproportion forces engineers to ditch lightweight materials as they scale up, swapping paper for brick, steel, and wood to support the massive increase in structural weight. This exact same math explains why our elephant-sized ant collapsed into dust. This diagram shows a cross-section of an insect's slender leg compared to its large spherical body. An insect's leg strength relies strictly on its cross-sectional area, while its overall body weight is dictated by its volume. The consequences of this battle between area and volume extend well past biology. We can see it in aerodynamics by dropping 2 different-sized toy helicopters from a high ledge. A falling object faces 2 competing forces. Gravity pulls it down based on its overall mass, which ties to its volume. At the same time, air resistance, or drag, pushes up against its exposed surface area to slow that fall. When released, the larger helicopter plummets past the smaller one. Its volume-based weight scales up so rapidly that it entirely overwhelms its area-based drag. Whether dictating the structural limits of an insect's limbs or determining how fast an object falls out of the sky, this inescapable mismatch between area and volume strictly governs our physical reality. Size is an absolute design constraint. It dictates what is physically possible in our universe. To scale an object or a living creature up to a massive size, you cannot simply magnify its existing proportions. You have to change its shape or the material it is made of to handle the new physical demands. This is why an ant survives with spindly, hair-like legs, while an elephant requires massive, pillar-like legs to move its immense bulk. A moment of wonder. The physical world looks the way it does because everything from microscopic insects to massive skyscrapers must find a way to function within the rigid boundaries of the square cube law.